Welcome to Selection Sort. Selection Sort divides the array into a sorted region and an unsorted region. On each pass, it scans the entire unsorted region to find the minimum element. That minimum is then swapped into the first unsorted position. After each pass, the sorted region grows by 1. Selection Sort always makes exactly n-1 swaps, regardless of the input. Let's watch it in action. Starting pass 1. Comparing 56 with the current minimum 44. 56 is not smaller, so the minimum stays at 44. Comparing 57 with the current minimum 44. 57 is not smaller, so the minimum stays at 44. Comparing 59 with the current minimum 44. 59 is not smaller, so the minimum stays at 44. Comparing 2 with the current minimum 44. 2 is smaller, new minimum found. Minimum found is 2. Placing it at the front of the unsorted region by swapping with 44. Swapped elements at positions 0 and 4. Element is now in its final sorted position. Starting pass 2. Comparing 57 with the current minimum 56. 57 is not smaller, so the minimum stays at 56. Comparing 59 with the current minimum 56. 59 is not smaller, so the minimum stays at 56. Comparing 44 with the current minimum 56. 44 is smaller, new minimum found. Minimum found is 44. Placing it at the front of the unsorted region by swapping with 56. Swapped elements at positions 1 and 4. Element is now in its final sorted position. Starting pass 3. Comparing 59 with the current minimum 57. 59 is not smaller, so the minimum stays at 57. Comparing 56 with the current minimum 57. 56 is smaller, new minimum found. Minimum found is 56. Placing it at the front of the unsorted region by swapping with 57. Swapped elements at positions 2 and 4. Element is now in its final sorted position. Starting pass 4. Comparing 57 with the current minimum 59. 57 is smaller, new minimum found. Minimum found is 57. Placing it at the front of the unsorted region by swapping with 59. Swapped elements at positions 3 and 4. Element is now in its final sorted position. Element is now in its final sorted position. Congratulations! You have successfully completed the selection sort lesson. Let's review what happened. The algorithm sorted the array in 4 passes. It made 10 comparisons. Each comparison checked whether a candidate element was smaller than the current known minimum. It performed 4 swaps, 1 swap per pass, to place the minimum element into its final position. The original array was 44, 56, 57, 59, 2. After sorting, the array became 2, 44, 56, 57, 59. Here are the key takeaways from this lesson. First, selection sort works by scanning the unsorted region each pass to find the minimum element, then placing it at the start of that region. Second, after every pass, the sorted boundary grows by 1 element. Selection sort always makes exactly n-1 passes. Third, in the worst case, the time complexity is order n squared. This happens when the array is sorted in reverse order. Fourth, the space complexity is order 1. It sorts entirely in place using only a few temporary variables, requiring no extra memory. Interesting insight, 4 swaps out of a maximum of 10 a typical average case run. Now let's explore the time and space complexity of selection sort in detail. Best case O, n superscript 2. Unlike algorithms with early exit optimizations, selection sort always performs n times n-1 over 2 comparisons regardless of input order. There is no early exit. However, it always makes at most n-1 swaps. Average case order n squared. For a randomly ordered array, selection sort still performs n times n-1 over 2 comparisons and exactly n-1 swaps. Unlike bubble sort, there is no difference in swap count between best, average, and worst case. Worst case order n squared. When the array is sorted in reverse order, comparisons are maximized at n times n-1 over 2. However, the swap count remains exactly n-1. Selection sort never performs more than n-1 swaps regardless of input. Space complexity order 1. Selection sort is an in-place sorting algorithm. It only needs a few temporary variables regardless of the input size. No auxiliary arrays are created. When should you use selection sort? Selection sort is a good choice for small datasets where write operations are expensive, because it always makes at most n-1 swaps, the minimum possible for any comparison-based sort. It is also excellent for teaching sorting concepts. When should you avoid selection sort? Avoid selection sort for nearly sorted data. Unlike bubble or insertion sort, it has no early exit optimization and always scans the full unsorted region. Also avoid it for large datasets above about 1000 elements, where its order n squared comparisons become too slow. That's everything about selection sort. Well done on completing this lesson.